A colossal stone pyramid rises from the desert, a silent witness to an ancient mind. An identical ambition built towering temples in distant jungles and on fertile river plains. What timeless engineering principles could possibly connect civilizations separated by oceans and thousands of years? This journey uncovers the hidden blueprint of human ingenuity that united Egypt, Mesopotamia, and Mesoamerica. You will discover a universal language of engineering that solved epic challenges in construction, water, and urban design. How did cultures with no contact arrive at such shockingly similar solutions? By the end, you will see these ancient wonders not as isolated mysteries, but as parts of a single, profound human story. What does our own modern world share with the architects of these timeless monuments? The very ground beneath their feet presented the first great puzzle. While separated by continents, the civilizations of Egypt, Mesopotamia, and Mesoamerica all faced a similar environmental equation. Life blossomed along the predictable floods of the Nile, the twin rivers of the Tigris and Euphrates, and the seasonal rains that fed the swamps and lakes of Mesoamerica. But this gift of water was a double-edged sword. The same floods that deposited rich, life-giving silt could also wash away homes and fields if left unchecked. The seasonal rains that filled reservoirs could lead to drought and hardship if not carefully stored. This created a powerful, shared necessity. To survive and thrive, these communities had to learn to work together on a scale humanity had never before attempted. They had to build canals to guide the water, dikes to control it, and storage systems to save it for drier times. This monumental task of managing a shared resource demanded new levels of social organization, creating leaders, planners, and the first true engineers. Out of this collective effort to harness nature, a blueprint for civilization itself was drawn, and from that shared foundation arose a stunningly similar answer to a new, even greater challenge: the need to build monuments that would touch the sky. The first principle they all mastered was the art of moving mountains, of shifting colossal weight with nothing but human ingenuity and simple physics. Thousands of hands worked in unison, moving mountains one stone at a time. This mastery of mass construction reveals a profound, shared insight. These ancient engineers understood that to build for eternity, they had to work with the earth, not merely against it. They selected materials not just for strength, but for what was available. The Egyptians harnessed the immense density of granite. The Mesopotamians perfected the art of sun-dried mud brick, and the Mesoamericans carved stubborn volcanic stone. Each substance presented a unique puzzle, yet the solution was always rooted in a universal grasp of simple physics. An inclined plane transforms an impossible vertical lift into a manageable, gradual ascent. A sledge gliding over a path of wet clay or rolled logs turns friction from a foe into an ally. A lever, placed at just the right point, allows a single individual to pivot a weight that would otherwise defy an entire team. This was not a story of brute force, but of brilliant, coordinated intellect. It was the world's first large-scale project management, directing the flow of labor, materials, and time with breathtaking precision. The silent, immovable mass of their pyramids and temples stands as a permanent record of that collective genius, but this physical achievement was only the beginning. Once they learned to touch the sky with stone, they had to find a way to speak to the heavens themselves, through a language written in angles, shadows, and light. The silent stones they so carefully placed were never meant to be mute. They were engineered to speak, to tell a story written in the language of the sun, the stars, and the sacred. Step inside the dim inner sanctum of an Egyptian temple, and you are walking into a specific moment in time, a chamber illuminated by a single shaft of light only on the day of a king's coronation. Climb the steep tiers of a Mesopotamian ziggurat, and you are ascending a stairway to the gods, a man-made mountain reaching for the divine. Stand atop a Maya pyramid at dawn on the winter solstice, and you witness the sun's rays align perfectly with the temple doorway, a cosmic event captured in stone. This was not coincidence, it was a deliberate, breathtaking form of communication. Their engineering was a sacred act, a way of weaving their understanding of the cosmos directly into the fabric of their cities. The very orientation of these structures was a form of celestial dialogue. The Great Pyramid of Giza is aligned with the cardinal directions with an accuracy of within a fraction of a single degree. The Pyramid of the Sun at Teotihuacan is positioned to mark the passage of the sun at key points in its annual cycle. These were not just tombs or temples, they were colossal calendars, permanent observatories that tracked the seasons, predicted the rains, and reaffirmed the cosmic order. The pyramidal form itself, emerging independently across the globe, is a powerful testament to a shared human instinct. It represents the primordial mound of creation, a sacred axis, a point where the human world could connect with the realms above and below. This profound integration of astronomy, theology, and stonework reveals a mind that saw no separation between the physical and the spiritual. To achieve such celestial precision, however, these architects needed a universal key, a silent language of numbers and lines that could translate their cosmic visions into immutable stone. This silent language of numbers and angles was the invisible blueprint for everything they built. Unroll a papyrus scroll from ancient Egypt, and you find meticulous calculations for a pyramid slope. Examine a Mesopotamian clay tablet, and it details the exact dimensions of a temple foundation. These civilizations spoke a universal dialect of precision, using standardized units like the royal cubit or the ninden. These were not rough estimates, they were the fundamental building blocks of their world, as reliable and universal as the meter or foot is today. With just a few simple tools, they translated this mathematical language into reality. A knotted cord stretched taut became a perfect measuring tape. A weighted plumb bob defined a true vertical line against a massive stone block. A simple sighting instrument, little more than two aligned sticks, could establish a perfectly straight foundation over vast distances. The result of this meticulous care was a structural harmony that has endured for millennia. The base of the Great Pyramid of Giza is leveled to within just 2 centimeters, a feat that would challenge modern engineers even with advanced technology. This was not about perfection for its own sake. It was about creating stability, about ensuring that a monument would stand not for a lifetime, but for all time. This precision also enabled modular construction, where thousands of identical bricks or stone blocks could be produced by different teams and still fit together perfectly, like pieces of a grand, preordained puzzle. Such a system, however, demanded more than just skilled surveyors. It required the power to feed, house, and direct thousands of workers for generations. The true masterpiece was not just the pyramid, but the organized society that could conceive of it and see it through to completion. This leads to a final, profound question. What common thread in the human spirit compelled these distant cultures to reach for the sky in such a similar, spectacular fashion? The true scale of their ambition becomes clear not in the silent stone, but in the organized chaos that brought it to life. A city of workers bustled at the foot of the Great Pyramid, a temporary metropolis dedicated to a single, monumental purpose. This was not a project built by slaves, but by a rotating workforce of thousands, a mix of skilled artisans and conscripted laborers fulfilling a form of civic duty. The same model of large-scale labor organization appeared along the Tigris and Euphrates, where crews maintained vast canal networks, and in the jungles of Mesoamerica, where communities assembled to erect their towering temples. The real engineering marvel was not just the structure, but the invisible system that made it possible. How do you feed 20,000 people for decades in the middle of a desert? How do you house them, manage their tools, and ensure a steady supply of stone, brick, and mortar? The answer was a revolution in social coordination. An advanced bureaucracy emerged, one that could keep meticulous records on clay tablets and papyrus, tracking everything from grain rations to the daily output of work gangs. This required a sophisticated logistics network, a supply chain that stretched across the kingdom to deliver food, water, and materials with the reliability of a modern engine. This ability to mobilize and direct human energy on such a colossal scale points to a profound level of social organization. It transformed collective labor into a powerful, tangible force that could shape the world. And the primary focus of this coordinated effort, the goal that truly sustained these civilizations, was not always a pyramid reaching for the stars, but something far more fundamental: the life-giving and unpredictable power of water. Water was the ultimate challenge, a force of both creation and chaos that demanded humanity's full ingenuity. To master it, these civilizations became hydraulic engineers of breathtaking skill. The Egyptians did not just wait for the Nile's annual gift of silt. They built a vast network of basin irrigation, a rhythmic system of canals and dikes that captured the floodwaters and distributed them with precision across their fields. This turned the entire river valley into a sustained, predictable engine of agricultural wealth. In Mesopotamia, the twin rivers of the Tigris and Euphrates were far less predictable, their floods capable of wiping out entire seasons of work. The response was an even more complex and permanent network of canals and dikes, a colossal public works project that tamed the wild waters and brought life to the arid plains. And in the seemingly impossible landscapes of Mesoamerica, where seasonal rains were followed by long dry periods, the solution was even more creative. The Maya built intricate reservoirs to capture every precious drop, while the Aztecs engineered floating gardens and aqueducts to supply their island capital of Tenochtitlan, a city built on a lake. In every case, the principles were the same. They understood slope and gravity, designing their channels so water would flow exactly where it was needed. They grasped the science of containment, building embankments strong enough to hold back immense pressure. This was not just farming, it was applied physics on a continental scale. The ability to guarantee a food supply transformed society itself. With the constant threat of hunger lifted, populations could grow and specialized roles flourished. This newfound security, this freedom from daily survival, allowed human energy to be directed toward a new and pressing need, the need to protect everything they had built. A city's walls were its first and most important line of communication with the outside world. To walk through the main gate of a Mesopotamian city like Ur was to pass through a statement of power, order, and collective security. These were not simple barriers of piled earth or stone. They were masterclasses in defensive architecture. Massive walls were punctuated by strategically placed bastions that allowed defenders to rain down projectiles on anyone attacking the gates. The gates themselves were complex, layered structures, often featuring multiple choke points and guard chambers designed to control and scrutinize every person entering the city. This sophisticated understanding of military engineering was not unique to the river plains. In Egypt, massive mud-brick walls enclosed temple complexes and royal cities, their sheer, intimidating faces a clear declaration of the pharaoh's might. In the jungles of Mesoamerica, Maya centers like Tikal were fortified with earthworks and palisades, protecting the sacred plazas and pyramids within. The fundamental principle was universal. Security was not an afterthought. It was the primary consideration from the very first sketch of the city's design. This need for protection shaped the entire urban landscape from the ground up. The streets of these ancient cities were not random paths worn by footsteps over time, they were deliberately planned. In many Mesopotamian and Mesoamerican cities, you find the world's earliest orthogonal grids, streets laid out in precise right angles. This was not merely for aesthetic appeal, it was a tool for social organization and control. A grid system made a city easier to navigate, to administer, and to defend. It created clear, defensible lines of sight and allowed soldiers to move quickly to any point of a breach. At the heart of this geometric order lay the central plaza, the public square flanked by the city's most important structures, the main temple and the royal palace. This layout was a physical map of the society's soul, placing the spiritual and secular rulers at the literal center of community life, surrounded by the orderly grid of neighborhoods that housed its citizens. The entire city became a model of the cosmos, a sacred, organized, and secure microcosm of the universe. To build a city that could withstand both time and conflict, these architects had to become masters of material science. They understood that a defensive wall was only as strong as the bricks that composed it. The Mesopotamians, lacking abundant stone, performed a kind of alchemy with the earth beneath their feet. They perfected the art of the mud brick, but they did not stop there. They discovered that by firing these bricks in kilns, they could create a building material of incredible durability, one that could resist weathering and even fire. In Egypt, builders mixed gypsum and lime to create the earliest forms of mortar and plaster, binding stones together and sealing surfaces against the elements. The Mesoamericans developed a concrete like stucco, a blend of lime and crushed stone, which they used to coat their pyramids and palaces, creating smooth, gleaming surfaces that have endured for centuries. This relentless innovation in creating lasting materials reveals a shared, long-term vision. They were not building for a single generation. They were building a permanent legacy in stone, brick, and mortar, a testament to a human spirit determined to create order and beauty in an unpredictable world. The desire for permanence demanded an almost alchemical knowledge of the earth itself. Under the harsh Mesopotamian sun, a simple mud brick might seem fragile, yet their engineers perfected its formula, mixing straw with clay to prevent cracking and firing it in kilns to create a ceramic shield against wind and rain. This was not just dried earth, it was a manufactured stone. In the limestone quarries of Egypt, workers did not merely cut blocks, they polished them to a fine tolerance, creating a seamless fit that locked the immense weight of a pyramid into a single, cohesive mass. Across the ocean, Mesoamerican builders coated their volcanic stone pyramids in a brilliant layer of lime stucco, a concrete-like innovation that protected the core from the relentless jungle moisture. Each solution was a masterclass in using local resources, but they all converged on the same profound goal: to cheat time itself. This required a deep, practical science. They learned through generations of trial and observation that a certain mix of lime and sand created a plaster that could breathe, preventing trapped moisture from shattering the stones from within. They understood that the compressive strength of a well-made brick pyramid could rival that of solid rock. This was not abstract theory, it was hard-won knowledge etched into every surviving wall. The longevity of their creation stands as a silent witness to this empirical genius, a legacy built not on secret formulas, but on a universal, relentless pursuit of endurance. This specialized knowledge, the understanding of material properties and construction techniques, became a sacred trust, meticulously passed from master to apprentice in a chain unbroken for generations. It raises a compelling question about the nature of innovation itself. Was this shared blueprint a product of cultural contact, or does it point to something far more fundamental about the human mind when faced with a universal challenge? The master architect stood at the intersection of all these principles, the living mind that unified celestial mathematics with the gritty reality of the quarry. In Egypt, the legendary Imhotep was not merely a royal builder. He was later deified as a god of wisdom, a healer, and a sage. This was the ultimate recognition of the intellectual power behind the stones. These architects were the original interdisciplinary thinkers, blending astronomy to align a temple, geometry to calculate a slope, theology to imbue the space with sacred meaning, and materials science to select the stone that would last for millennia. Their role was to hold the entire cosmic and practical blueprint in their mind before a single foundation trench was dug. This deep, specialized knowledge was a form of power, often carefully guarded within scribble schools or priestly orders. It was transmitted through rigorous apprenticeships, where a young student would learn not only how to draw a perfect right angle with a knotted cord, but also the sacred formulas and ritual protocols that made the construction a holy act. The emergence of this professional class signals a profound shift in human organization. It reveals a society that consciously invested in expertise, that understood that the grandest visions required the most meticulous calculations to become real. These individuals were the bridge between the abstract and the tangible. They took the universal language of physics and mathematics and gave it a local dialect, expressed in the distinctive profile of a Maya corbel vault or the precise batter of an Egyptian pyramid wall. Yet their genius was always in service to a larger cultural narrative. The architect did not build for personal glory, but to give physical form to a community's deepest beliefs about the cosmos, the gods, and their place within the natural order. This fusion of technical skill and spiritual purpose is what separates a mere pile of stones from a monument that speaks across centuries. A stone was more than just a building block, it was a prayer. The immense labor of moving millions of tons of material was not driven by economics alone, but by a profound cultural imperative. For the Egyptian pharaoh, the pyramid was a machine for resurrection, a ramp to the stars. For the Mesopotamian priest-king, the ziggurat was a physical ladder connecting heaven and earth. For the Mesoamerican ruler, the pyramid was a sacred mountain anchoring the cosmic order. The engineering was the ritual. The precise placement of a cornerstone was a ceremonial act, often accompanied by offerings and blessings. The specific number of tiers on a ziggurat corresponded to the known planets or levels of the cosmos. The exact alignment of a temple doorway to capture the solstice sun was a form of dialogue with the gods. This turns our modern understanding of a construction project completely on its head. The building site was a temple, the workers were worshippers, and the architect was a high priest interpreting a divine blueprint. The project's timeline was often dictated by celestial cycles, with construction phases initiated on auspicious dates tied to a king's coronation or a major religious festival. The very act of building, the communal effort of raising a monument to the heavens, was as vital to the society's spiritual health as the finished structure itself. This cultural engine provided the unstoppable motivation required to attempt the impossible. It transformed a daunting logistical task into a sacred duty, fueling generations of labor with a purpose that far exceeded mere survival. This spiritual drive to build raises a final, haunting question about the legacy they left behind, not in stone, but in the very mind of modern humanity. The true genius of these ancient engineers is revealed not in their similarities, but in their brilliant adaptations. While a shared blueprint guided their ambitions, the materials and methods they employed were a direct conversation with the land itself. In Egypt, the challenge was the sheer, unyielding mass of stone. The predictable, gentle floods of the Nile provided a stable agricultural base, freeing immense labor forces to perfect the art of quarrying and moving granite and limestone. Their entire architectural language was written in the grammar of megaliths. Travel to Mesopotamia, and the equation changed completely. Here, stone was scarce, but the twin rivers provided an endless supply of alluvial mud. The engineering response was an ingenious pivot, a mastery of the sun-dried and kiln-fired mud brick. This was not a compromise, it was an innovation that allowed them to build colossal ziggurats and sprawling city walls from the very earth beneath their feet, creating a civilization of clay that rose from the river plains. Then, across the ocean, the Mesoamericans faced a different world altogether, one of volcanic stone and intense seasonal rains. Their answer was a stunning synthesis, combining the carving of stubborn basalt with the invention of lime stucco and early forms of concrete. They learned to seal their structures against the jungle's humidity, creating gleaming white pyramids that acted as both temples and vast, engineered catchments for precious rainwater. In every case, the principle was the same: work with what you have. Their engineering was not about imposing a foreign template upon the landscape, but about listening to it and responding with breathtaking creativity. This adaptive intelligence was the key to their longevity, proving that the most enduring solutions are not forced upon an environment, but emerge from a deep and respectful dialogue with it. This legacy of localized ingenuity begs a final, powerful question about the echoes of this ancient blueprint in the world we are building today. These structures were not just aligned with the stars, they were engineered to track them. The Great Pyramid of Giza does not merely face north. Its sides are oriented to the cardinal directions with an accuracy finer than 1/15th of a single degree. This was not a symbolic gesture, but a feat of precision surveying that would have required years of meticulous nightly observations. Centuries later and across the globe, the Maya designed the Colossal Observatory at Chichen Itza with narrow, strategically placed windows. These apertures were not random openings, they were precisely calibrated sightlines that framed the extreme positions of Venus in the night sky. To the Maya, Venus was not just a bright light, it was a deity associated with war and rain, and its movements dictated the timing of military campaigns and agricultural cycles. Even the massive ziggurats of Mesopotamia were carefully oriented to celestial phenomena, their stairways and corners acting as fixed reference points against the moving heavens. This principle goes far beyond simple sky watching. It represents the engineering of time itself. By embedding their astronomical knowledge into the very fabric of their cities, these civilizations created perpetual stone calendars. A shaft of light falling on a specific glyph only on the summer solstice, a shadow that precisely bisects a stairway on the equinox. These were not accidents. They were deliberate mechanical events, a form of clockwork built on a monumental scale. This integration of science and sacred space allowed them to mark sacred dates, regulate planting seasons, and demonstrate a profound belief in a cosmic order that could be understood, predicted, and reflected in their architecture. This celestial rhythm even dictated the pace of their construction. Major building phases were often initiated on astronomically significant dates, linking the growth of a pyramid or temple to the eternal cycles of the cosmos. The project itself became a ritual in time, a physical manifestation of a society moving in harmony with the universe. The true scale of their ambition is measured not in stone but in generations. A single king might lay the foundation of a pyramid, knowing full well his grandson would be the one to cap its summit. This was the ultimate test of an engineer's vision, a project plan that had to outlive its original architect. How do you maintain the precision of a design over a century of construction? The answer lies in the silent language of the stones themselves. Quarry marks and foundation deposits acted as instructions for the next crew, a permanent record of alignment and intent. At the Great Pyramid Complex of Giza, archaeologists have uncovered the remains of a vast, organized settlement, a purpose-built city for the rotating workforce. This was not a temporary camp, but a permanent logistical hub that functioned for decades, managing the flow of food, tools, and thousands of skilled laborers. The project was broken down into manageable stages, each with its own clear goal. The first phase might be the leveling of the bedrock foundation, a task requiring astonishing accuracy. Next came the construction of the inner core, followed by the meticulous placement of the outer casing stones. Each stage required different skills, different materials, and a different organization of labor. This phasing allowed for continuous progress, even as individual workers came and went, fulfilling their seasonal duty. It also created a powerful, self-perpetuating system. A young man might start his service hauling stones for the foundation, and years later, return as a skilled mason to dress the upper courses, teaching his own son the craft in the process. The project itself became a living tradition, a cycle of knowledge and labor that bound the community together across time. This required a form of foresight we can scarcely comprehend today, a collective commitment to a future they would never personally witness. What force could possibly sustain such a patient, monumental effort across the fleeting span of human lives? A single stone carved with a falcon or a jaguar was not merely decoration, it was a fragment of a shared dream. These grand projects were the crucibles in which civilization itself was forged. A farmer from a distant village, contributing his labor to the pharaoh's pyramid, was not just moving stone, he was participating in the divine order. A baker supplying bread to the workers at a ziggurat was helping to build the very ladder that connected his city to its protector god. Through this shared, monumental effort, a collection of disparate clans and villages could transform into a unified people with a common identity and a collective purpose. The engineering marvel was, in itself, the most powerful political statement a ruler could make. It demonstrated an ability to command resources and labor on a godlike scale, proving the ruling class's legitimacy and power not through words, but through undeniable, sky-scraping achievement. This was nation-building made literal, stone by stone. The very act of construction became a ritual that bonded the community, turning the pyramid or temple into a permanent symbol of their united strength. To walk through the shadow of such a structure was to be reminded of what could be accomplished together. This collective identity was then reinforced by a universal visual language. The same symbols of power and piety, the same scenes of gods and kings, were repeated on walls from the Nile to the Euphrates to the Yucatan. A visitor from one Maya city would understand the cosmic symbolism carved into the stones of another, just as an Egyptian would recognize the meaning behind the falcon and the serpent on a distant temple wall. This shared iconography created a cultural cohesion that transcended local dialects and rivalries, uniting vast regions under a single ideological banner. The stones did not just house gods, they taught a consistent story about the world, the cosmos, and everyone's place within it. This profound unity of purpose, this fusion of spiritual belief and social organization, may be the most powerful engineering principle of all, one that continues to shape our world in ways we are only beginning to understand. A stone column shaped like a lotus blossom does more than simply hold up a roof. It tells a story of creation rising from the primordial waters. This was the essence of their genius, a world where the practical and the profound were inseparable. The engineer and the artist were the same mind, and every structural element was an opportunity for symbolic expression. In Egypt, the massive pillars of Karnak are not just posts of stone, they are forests of stone papyrus and lotus, transforming the temple into a microcosm of the natural world where the gods resided. The carved figures of pharaohs smiting their enemies on the outer walls were not mere decoration. They were an integral part of the building's defensive magic, a perpetual ritual of protection woven into the very skin of the structure. In Mesopotamia, the ziggurat was not a blank monolith. Its towering facades were a brilliant mosaic of glazed bricks in lapis lazuli blue and fiery orange, gleaming in the sun like a celestial mountain. Each colored brick was a pixel in a vast, symbolic image, and the structure's sheer, intimidating presence was amplified by this radiant, otherworldly skin. Walk through the plazas of a Maya city, and you are surrounded by a living text. The sides of pyramids are not flat surfaces. They are cascades of intricate stone mosaic depicting serpent deities, cosmological maps, and the histories of dynastic rulers. The stucco masks flanking the stairways are not attached. They are carved directly from the core masonry, their immense weight and form part of the pyramid's own structural identity. This integration meant the art could not be removed without causing the building to lose its meaning, and perhaps even its stability. The vibrant paints that once covered these stones, now faded by time, engaged every sense, turning the city into a multi-sensory experience of power, belief, and identity. The rhythmic repetition of symbols on a frieze, the hypnotic patterns of a mosaic, all served to reinforce a shared cultural story for every person who lived there. This was engineering as a total environment, designed not just to be seen, but to be felt and understood on a deep, instinctual level. In this world of stone and symbol, the very act of recording knowledge had to be as permanent as the monuments themselves. A master builder's most vital tool was not his measuring cord, but his student. The precise formula for a durable lime plaster, the exact geometric rule for a pyramid's stable slope, this was knowledge too precious to be left to chance. It had to survive its creator. This demanded the invention of the first knowledge economy, a robust system for transmitting expertise across the fleeting span of human lives. At its heart was the intimate bond of the apprenticeship. A young scribe in Egypt would spend years at the side of a master, learning not only how to calculate the volume of a stone block, but also the sacred rituals that sanctified its placement. In Mesopotamia, a student in the tablet house would practice drawing intricate temple plans on wet clay, his work preserved for future builders to study. This was a chain of wisdom, linking one generation to the next through direct, hands-on instruction. But human memory alone was not enough. These cultures created the world's first technical manuals, detailed schematic drawings on papyrus scrolls and clay tablets that served as permanent references. A single drawing could specify the dimensions of a column, the profile of an arch, or the layout of an entire city's water channels. Temples and royal libraries became the hard drives of the ancient world, guarded repositories where these schematics were stored, copied, and studied. This intergenerational engine of learning allowed for cumulative innovation. A builder in the 18th dynasty of Egypt could study the plans of a pyramid built 500 years earlier, understand its strengths, and refine its design. This is how core principles became timeless, not through a single flash of genius, but through the patient, collective work of centuries. Yet this delicate chain was sometimes broken. A library burns, a dynasty falls, a master dies without passing on his final secret. It is in these silences, these gaps in the transmission of knowledge, that the deepest mysteries of the ancient world were born, leaving behind monuments so perfect we still question how they were ever made. Even their most silent stones guard secrets we have yet to fully unravel. We can calculate the immense weight of a pyramid's capstone, that final, crowning piece set hundreds of feet in the air, but the final act of its placement remains one of history's most captivating puzzles. Did they construct a spiraling earthen ramp that was later dismantled, its traces erased by desert winds? Or did they employ a clever system of counterweights and levers, a method so straightforward it was never deemed worthy of recording? These are not questions about their limitations, but about the depth of their practical wisdom. Their methods were so refined, so integrated into the daily rhythm of their work, that the greatest tricks of their trade may have been passed down through silent demonstration, never making it onto a clay tablet or papyrus scroll. This same quiet genius echoes in the vast, open landscapes they surveyed. How did an Egyptian engineer, with simple sighting tools, achieve an alignment so perfect that the sides of the Great Pyramid deviate from true north by less than a fraction of a single degree over its entire mile-long base? The precision is so acute it feels almost supernatural, suggesting a familiarity with the stars and the measurement of shadows that we can only partially reconstruct. Perhaps the most compelling mystery lies in the tools we have never found. Were there specialized instruments crafted from wood and cord that simply returned to the earth, leaving no trace for modern archaeologists? The absence of evidence is not an empty void, but a space filled with possibility, pointing to a level of sophistication that was both profound and, in some ways, ephemeral. Investigating these gaps inevitably leads to a grander, more controversial question. Could there have been a faint, almost imperceptible thread of connection across the oceans? While no evidence suggests direct contact, the parallel development of such specific ideas, the pyramidal form, precise celestial alignment, and complex water management, invites us to wonder about the universal patterns of the human mind when faced with identical challenges. Are we seeing independent inventions or echoes of a foundational knowledge that traveled in ways we cannot yet see? These enduring mysteries do not diminish their achievements. They transform these ancient sites from static ruins into living conversations, challenging us to look deeper and recognize that the story of human ingenuity is far from complete. The enduring mystery of these parallel inventions forces a difficult question upon us. Did these blueprints for civilization travel, or did they simply emerge from the same wellspring of human need? The theory of cultural diffusion suggests a single, brilliant idea journeying across continents, passed from one culture to the next like a whispered secret. Imagine a fundamental concept, perhaps the very principle of the pyramid, carried by intrepid travelers along ancient trade routes, slowly making its way around the world. It is a compelling vision, a story of connection that ties humanity together. Yet the evidence for such direct, long-distance contact between the Nile and the Maya lowlands remains frustratingly absent from the archaeological record. There are no shared artifacts, no linguistic echoes, no artistic styles that convincingly bridge the vast ocean between them. This leaves us with a powerful alternative, the principle of convergent evolution. In nature, a shark and a dolphin develop similar streamlined bodies, not because they share a common ancestor, but because that shape is the optimal solution for moving swiftly through water. In the same way, these ancient societies, facing the universal challenges of controlling water, organizing labor, and reaching for the divine, may have simply arrived at the same optimal answers. The pyramid form, for instance, is not just a spiritual symbol. It is the most stable and logical way to build something incredibly tall and heavy with simple technology. The question then becomes not who invented it first, but what fundamental laws of physics and society guided them all to the same brilliant conclusion. To solve this puzzle, we must look past the grand monuments and examine the finer details of their technological toolkits, the specific choices they made when faced with a practical problem. A copper chisel's edge meets stubborn limestone with a precise, ringing blow. In another desert, a team of workers positions a wooden lever, pivoting a massive mud brick into place. And deep in a jungle quarry, fire crackles against a granite face, followed by a splash of water that exploits microscopic fractures to split the stone. These are the sounds of three different worlds solving the same equation. The Egyptians refined copper and stone, the Mesopotamians mastered the lever and the ramp, and the Mesoamericans, without metal tools or wheeled carts, turned fire and water into their primary instruments. At first glance, their toolkits seem worlds apart, a hierarchy of technological progress. But look closer, and the real principle emerges. It was never about the sophistication of the tool itself, but about a universal grasp of physics. Leverage turned immense weight into manageable force. The inclined plane conquered gravity by trading a steep climb for a longer, gentler path. Even the Mesoamerican technique of fire setting was a brilliant manipulation of thermal expansion, using nature's own laws to do the work of a metal pick. This reveals a profound truth about human ingenuity. Monumental achievement does not require secret technology or lost sciences. It flourishes where there is a deep understanding of simple, available principles and the social organization to apply them on a grand scale. The true engine was not the copper chisel or the wooden sledge, but the coordinated will of thousands of hands and minds, all directed by a shared vision. The most advanced tool in their arsenal was, and always has been, the organized human community. The true cost of a pyramid was not measured in stone but in grain. Who paid for these colossal endeavors? The answer lies in the world's first complex economies, systems that transformed the raw energy of the sun and soil into monumental architecture. These were not projects funded by a royal treasury in the modern sense, but by the entire agricultural engine of the state. A farmer's harvest was not just food for his family, it was a form of currency. A portion of his yield, his tax, was collected in vast state granaries. This stored wealth, this agricultural surplus, was the fundamental fuel that powered the entire enterprise. It fed the army of skilled artisans who carved the stones, the engineers who designed the ramps, and the laborers who hauled the blocks. It supported the scribes who kept the accounts and the overseers who managed the work gangs. This system created a new class of people who did not grow their own food, but whose specialized skills were dedicated entirely to the act of creation. The entire society was reorganized around this single, monumental purpose. The wealth generated by carefully managed fields and long-distance trade routes was meticulously funneled by the ruling elite into these constructions. This required a stable and incredibly productive economy, one that could reliably produce more food than its people needed to survive from one season to the next. But this flow of resources was not a one-way street. The construction project itself became a powerful economic stimulus. It created immense demand for raw materials like timber, copper, and stone, spurring mining and quarrying industries. It required transport, leading to the building of roads and cargo boats. It needed vast quantities of food, clothing, and tools, energizing local markets and crafts. This created a powerful feedback loop. A successful harvest meant more taxes, which meant more workers could be employed on the pyramid. The progress of the pyramid, in turn, demonstrated the ruler's divine favor and political power, which reinforced the system of taxation and social order that made the next harvest possible. The sheer scale of this continuous investment, sustained for generations, reveals the immense central authority wielded by these early states. It was a grand bargain between the ruler and the ruled, an exchange of grain and labor for divine protection, national pride, and a permanent place in the cosmos. This economic engine, however, required one final, crucial component to function: a system of record-keeping so precise it could account for every brick, every bushel of grain, and every day of labor. For the common farmer, the pyramid's shadow was a familiar part of the horizon. This was not a distant spectacle, but a structure built with the sweat of their own hands, a tangible presence in their daily existence. Every year, when the floodwaters receded and the fields were prepared, a different kind of season began. A call would go out for laborers, and individuals would travel to the great building sites to fulfill their civic duty. This was not a life of hardship, but a form of national service. The state provided their sustenance with rations of bread, beer, and fish drawn from the vast central granaries. For a few months, a farmer could become a stone hauler, a craftsman's assistant, or a water bearer, working alongside thousands of others in a shared, monumental endeavor. This rotation wove the grand project directly into the fabric of their annual cycle, making the growth of the monument a personal experience. The very food they ate was tied to its progress. This system transformed abstract state power into a daily reality of community and shared purpose. The spiritual impact was even more profound. The local temple was the heart of their village, but the distant, gleaming pyramid on the horizon was the axis of their entire universe. It was a permanent reminder that their king was a living god, a guarantor of the cosmic order that brought the annual flood and made their crops grow. Their labor was not just a tax, it was a prayer in physical form, an investment in maintaining the harmony of the world itself. This connection gave every individual a defined and vital role in a story much larger than their own life. The practical benefits of these grand projects also quietly filtered down to their fields. The same master surveyors who laid out a temple's perfect foundation also applied their skills to redesigning irrigation canals, making them more efficient and reaching more land. The advanced understanding of hydraulics used to supply a massive workers' city could be adapted to create smaller, local reservoirs protecting villages from drought. The stoneworking techniques perfected for royal tombs found new uses in stronger, more durable millstones for grinding grain. This trickle-down of innovation meant that the elite's obsession with eternity ultimately yielded tools that improved the common person's prosperity and resilience. The grand principles of engineering, born from the ambition of kings, ultimately helped to build more stable, more productive, and more meaningful lives for the citizens who made it all possible. Even the most brilliant engineering knowledge is fragile, dependent on the society that sustains it. The great civilizations of the ancient world eventually faced periods of decline, and the fate of their technical wisdom varied dramatically. In Mesopotamia, the intricate system of canals and the precise formulas for fired brick were gradually lost as empires fragmented and great urban centers were slowly reclaimed by the desert sand. The social machinery that coordinated thousands of laborers and maintained meticulous records on clay tablets simply ceased to function. In Egypt, the knowledge proved more resilient, passed down through priestly lineages and transformed over millennia, its core principles adapted by successive cultures but never entirely forgotten. Meanwhile, in Mesoamerica, the collapse of major Maya city-states did not erase their innovations. Instead, successor cultures, including the Aztecs, carried forward and refined principles of hydraulics and urban planning, building upon the foundations of their predecessors. This uneven survival reveals a profound truth that specialized knowledge is not self-sustaining. It is a delicate flame requiring the fuel of stable institutions, organized education, and economic surplus to keep burning. When the complex political and social structures that nurtured these engineers crumbled, their most advanced techniques often faded from memory, and yet the structures themselves refused to disappear. The silent, enduring pyramids, the vast irrigation channels etched into the landscape, these became the teachers. They stood for centuries as undeniable proof of what was possible, inspiring awe and a relentless curiosity in all who encountered them. Their sheer physical resilience is the ultimate validation of the timeless principles used in their creation, a permanent invitation for future generations to learn their secrets anew. Their silent endurance through millennia has become a modern classroom. When archaeologists first cleared the sands from the base of the Great Pyramid, they were not just uncovering a tomb, they were opening a textbook on structural engineering. The principles these ancient builders arrived at through empirical trial and observation are now being validated by advanced computer modeling and material science. The pyramid itself, that most iconic of forms, offers a masterclass in stability. Its wide base and gradual taper distribute immense gravitational loads with breathtaking efficiency, a principle now applied in the design of modern skyscrapers and earthquake-resistant structures that must sway without shattering. The ancient engineers understood load paths intuitively, channeling weight down into the earth in a way that has resisted even major seismic events for thousands of years. This is not just history, it is a living science. Contemporary architects looking to reduce a building's energy consumption now study the passive ventilation systems found in ancient Persian wind catchers or the thermal mass of thick Egyptian stone walls, designs that cool and heat interior spaces without a single watt of electricity. The quest for sustainability has sent researchers back to these sites, analyzing how entire cities were oriented to capture cooling breezes, or how complex aqueducts and cisterns managed water with a precision that put some modern systems to shame. In our laboratories, we now decode the chemical secrets of Roman concrete that actually grows stronger in seawater, or the lime plasters of the Maya that have withstood jungle humidity for over 1,000 years. We are realizing that their empirical knowledge of material properties, gained over generations of careful observation, holds clues for creating more durable and environmentally friendly building materials today. This long-term perspective is perhaps their greatest gift to our often short-sighted world. They engineered for eternity, choosing materials and designs with a focus on permanence that we are only now relearning in our search for sustainable solutions. The ancient master builder who unified celestial math with gritty practicality was indeed the first civil engineer. Their legacy challenges us to look beyond mere efficiency and to build with a wisdom that honors both the environment and the enduring spirit of human ingenuity. Their legacy of endurance is a direct challenge to our modern throwaway culture. While we grapple with the consequences of climate change, these ancient builders offer a masterclass in environmental harmony. They saw their landscape not as an obstacle to be conquered, but as a partner in a grand, collaborative project. Their entire approach to water was a lesson in listening to natural cycles. Instead of fighting unpredictable floods, the Egyptians developed basin irrigation to work with the Nile's annual rhythm, capturing its gift of silt and water to sustainably enrich their fields for thousands of years. In the arid plains of Mesopotamia, the extensive canal networks were designed not just to bring water in, but to prevent salinization, a delicate balancing act that preserved the long-term health of the soil. This was engineering for permanence built on a deep, observed understanding of local ecology. Their architectural genius extended to the very air they breathed. The massive stone walls of an Egyptian temple or a Maya palace acted as a natural thermal battery. The thick masonry would absorb the heat of the day, keeping interior spaces cool, and then slowly release it during the cooler nights, creating a stable, comfortable environment without any need for external power. Structures were strategically oriented to catch prevailing breezes, creating passive ventilation systems that refreshed entire complexes. This profound connection between engineering and well-being meant that a well-designed building was, by its very nature, a healthy one. Perhaps their most timeless principle was the reliance on local materials. The Egyptians used the limestone plateau of Giza itself. The Mesopotamians built their world from the mud beneath their feet. The Mesoamericans quarried the volcanic stone of their highlands. This drastically reduced the energy required for transportation and ensured that their structures were inherently suited to the local climate and geology. They were not importing foreign solutions, they were cultivating a deep, responsive dialogue with the place they called home. This holistic view, where engineering was inseparable from environmental and human health, stands as their most urgent lesson for our time. It invites us to ask whether our own monuments of glass and steel, for all their brilliance, are built with the same wisdom for the long term. A clean stone aqueduct carried fresh spring water into the heart of Tenochtitlan, while a parallel network of canals efficiently carried waste away from its densely packed neighborhoods. This was urban planning as a form of preventative medicine. Without any knowledge of microscopic pathogens, these ancient engineers intuitively understood the vital link between clean environments and community health. Their sophisticated water management was the first line of defense against illness. In Egypt, the same mathematical precision used to align a pyramid was applied to excavate deep, protected wells and design drainage systems that kept living spaces dry and sanitary. In the Indus Valley, another early cradle of civilization, Entire cities were built with complex covered drains and bathrooms connected to a central sewer system. These were not isolated projects but foundational components of city design. By systematically separating clean water from waste, they were actively combating the spread of waterborne diseases. This engineering foresight had a direct and profound impact on the growth of society itself. A city that could reliably provide fresh water and manage sewage could support a much larger, more stable population. It reduced the constant threat of outbreaks that could decimate a community, allowing for greater social complexity and the flourishing of arts, governance, and specialized trades. This concern for communal well-being reveals an integrated worldview, where the health of the body politic was as important as the stability of a temple wall. The engineer and the city planner were, in a very real sense, early public health officials. Their legacy is a powerful reminder that the greatest monuments to human ingenuity are not always the ones that reach for the heavens, but often the invisible systems that silently sustain life below. A perfectly level foundation, a pyramid's precise slope, the timing of a celestial event, all were written in a silent, universal script. These architects were fluent in the language of mathematics, a dialect of number and form that echoed across continents. They consistently employed specific ratios, like approximations of pi and the golden ratio, not as mere decoration, but as the core structural logic of their designs. The very shape of a pyramid is not a cultural preference. It is a direct consequence of physical law, the most stable form for distributing immense weight with the materials they had. This reveals a stunning truth: the principles they used were not invented but discovered. They were uncovering the fundamental rules of the universe itself. Geometry gave them the power to survey vast tracts of land after the annual flood, to lay out a city grid with perfect right angles, and to calculate the volume of a stone block with unerring accuracy. Arithmetic was the engine of their logistics, allowing scribes to account for thousands of workers, to track rations of bread and beer, and to manage the flow of materials over decades of construction. This shared mathematical foundation is the deepest link of all. It means that an Egyptian engineer calculating the angle for a ramp, a Mesopotamian scribe determining the volume of a grain silo, and a Maya astronomer predicting the cycle of Venus were all reading from the same cosmic textbook. Their tools and symbols were different, but the truths they recorded were identical. This universal language of numbers and forms allowed them to translate a grand vision into an immutable, physical reality, proving that the blueprint for civilization was written into the very fabric of the world they sought to build. A modern construction crane can lift several tons of steel with the push of a button, yet the structure it helps build may be designed to last only a century. The Great Pyramid of Giza was raised with nothing but copper chisels, wooden mallets, and rope, and it has already endured for over 4,500 years. This stark contrast forces a difficult question: which system represents the more advanced technology? Our modern perspective often equates advancement with complexity and power, leading us to label these ancient methods as primitive. But this is a profound misjudgment. Their technology was not a crude first attempt. It was a perfectly adapted solution. It was a sophisticated response to a specific set of constraints, available materials, and cultural goals. They did not have industrial machinery, so they perfected the physics of the lever and the inclined plane. They did not have digital surveying tools, so they developed an uncanny mastery of astronomy and geometry to achieve alignments within a fraction of a degree. The true measure of their technology is not its simplicity, but its breathtaking results. We struggle today to create concrete that does not crumble in decades, while their lime plasters and stonework have withstood millennia of wind, rain, and seismic shifts. This was not a lack of knowledge, it was a different kind of knowledge, one deeply rooted in long-term thinking and a harmonious relationship with the natural world. To call their work primitive is to miss the point entirely. Their intelligence was not a precursor to our own. It was a parallel and equally brilliant branch of human ingenuity. They solved the same fundamental problems of stability, precision, and endurance, and they did so with an elegance that modern engineering is only now beginning to fully appreciate. When we look at these ancient wonders, we are not looking at the infancy of technology. We are looking at a mature, refined, and supremely successful technological tradition that has much to teach us about building for the ages. From the banks of the Nile to the plains of Mesopotamia and the highlands of Mesoamerica, a single story echoes across the ages. We have journeyed through a world united not by trade routes or empires, but by a shared blueprint of the human mind itself. These cultures, separated by vast oceans and thousands of years, all arrived at the same profound solutions. They mastered the movement of colossal weight, spoke a language of celestial alignment written in stone, tamed the power of water, and orchestrated the collective effort of thousands. This was not mere coincidence. It reveals a universal logic, a deep-seated human instinct to solve epic challenges through a blend of fundamental physics and breathtaking creativity. The true innovation was not a secret tool or a lost science, but a way of thinking. It was the ability to observe the world, understand its core principles, and then apply them with unwavering collective purpose. Their legacy is far greater than the silent, enduring stones they left behind. It is the enduring power of human cooperation and ingenuity, a testament to what we can achieve when we work together toward a common vision. These ancient wonders stand as a permanent reminder that the greatest challenges of building a sustainable, meaningful, and beautiful world are not new. They connect us across the ages, inviting us to learn from the timeless wisdom etched into the very landscape of our past. If this exploration of our shared human story has sparked your curiosity, we invite you to subscribe for more journeys into the world's greatest historical mysteries. We would love to hear your thoughts in the comments below. Which of these ancient engineering principles do you find most astonishing?